Let me just write the questions. Okay. Okay, because we know that we are in the improper integral. Okay, so these integrations will be improper, and on some x, the functions will be discontinued, right? Will be discontinued. So I think if we plug in 0, that will be discontinued, right? If we check 0 inside the function, right? Okay. At x, or maybe write first, let f of x is e at x equals 0, f is undefined. You can write. Or if you want, you can directly write down the limit, because when x is 0, it will be undefined. So limit from the right as the left, right? Because it has -1. So we can say st approaching 0 from the left. Okay. We can have integrations -1 e 1 over x, or let me just write the whole thing first. Okay. Okay. The improper integral, we are just looking at using the limit, right? But the rest of the questions, we need some techniques of integration that we have learned also. Okay. So my idea is, you can write down this integral in separate layers and try to work that out. And later, when we have the results, we can plug into here, and we can use the interval -1 to t, and then evaluate the last one, evaluate the limit. Okay, so there is at least 3 steps in solving this problem. Okay, you can still, if you want to directly write in terms of limit, you can write limit and then you try to solve this in one direction. But usually my suggestion is you can take out this integral and solve the integral first, and later put it back to the limit. Right? Okay, let's write first our integrations. Okay, so let's have just an indefinite integral first. Okay. Evaluate this. Okay, what will happen? What do we do first to solve? Any idea to solve this? Okay. I think if you look here, 1 over x. Okay. If you look here, this is x cubed. Okay. If we think, maybe if we can separate the x cubed, become x and x squared. Okay. And maybe, is there any relation 1 over x with the 1 over x squared? Derivative, right? The derivative, right? So probably that will be one way to see the pattern. So we can try to write down 1 over x. and then e 1 over x, and then 1 over x squared dx. Okay? So we can try to break down this first. And then maybe we can try from here and try to derive this and become negative 1 over x squared dx. And we have the dx is negative x squared du. So it's basically saying that we can cancel the x squared, this one, okay, and put the negative, right? Okay. So I think we can start doing that. So we can take the 1 over x as u, e with u, and then this will be having a negative. Oh, I forgot to write the negative. Let me write negative at the front like that, and du. Okay. Now, as you remember, as I mentioned the first time about the integration by parts, this form is basically the easiest form, one of the easiest form that we can integrate using integration by parts. You see the variables, right? You see the x or x squared, x cubed, and you see another element is e, which is if you integrate or derive, it will be stay like that. Yeah, right? So we can check this. We can derive this, right? We can integrate this, and we can use integration by parts. Okay. So let's do some integration by parts. Okay, because it's 0, so we can skip that part. So we will have minus u e u minus e u, or in our case, uh, this will be EU minus EU plus. Let's say plus C first, okay? Okay, now to solve this, we can exchange all the, maybe I will write here, limit as t approaching 0 from the negative. Let me write the whole thing from -1 to t e 1 over x, x cubed. We can write still, and we can exchange the endpoints. Let's write in terms of u. So if u is 1 over x, so when x is -1, u is -1, right? And when x is t, then u will be 1 over t. So we can exchange with -1 and 1 over t. And we can write down this become negative u eu du and write down our solutions, which is we still need to write the limit and then write down EU minus U EU, and write down this is from 1 to 1 over t. And we can solve this limit. Okay, I think we can still solve this. Let me exchange this with the negative. Okay, and let 1 over t is equal some s. Okay, when t is getting 0, s is getting negative infinity, right? From the 1 over x function. So limit this will be s negative 1 e s. We can write our in terms of s and exchange all. Okay. Okay, this part here, if we try to divide all by s, or if we look here, it will be infinity over infinity, seems right. We can have some L'Hopital. We can have some L'Hopital, and this will be 1 over negative e negative x, and this is limit s. So this will be 0, right? This will be 0 when you plug in here, right? So this will be equal negative 2 over e, and we can say that the limit is converges. Okay. So yeah, I think, like I said before, to solve a problem in the integral, you need at least the concept of limit and then L'Hopital, which includes the derivative, right? So indirectly, you need to learn from every chapter. But the focus on the problem is the question in the integration. Okay? But to integrate the or the technique that we need, it will include some derivatives, right? Okay. Yes, it's quite long for just a short questions. It's just asking this, but we need to use really, yeah, really long and a little bit complicated in the process. Okay. Okay, let's continue a little bit. And the last section on the chapter 7 and the improper integral is, we called it the comparison theorem. And this theorem is useful when you can compare some unknown integral with other integral that you know, whether it is converged or diverged. And then you can tell the unknown will be converged or diverged based on the other integral. Okay, let's start with the suppose we have f and g, both are continuous functions. Okay, the statement, first statement, let's take the f of x is greater or equal g of x, and this is greater or equal 0. For x greater or equal a is a real number. So first, if we have a setup of integrals from a to infinite of f of x dx, if we know that this is converged or convergent, then by this theorem, because we know that the f is greater than g, then this will also converge. Okay, this is the first statement. The second statement, okay, if now we start with g. If g divergent, okay, then for sure, okay, then the f also divergent. Okay, so f greater than g greater than 0. If the integral of f converge, okay, because f is greater than g, of course the integral of g will also converge. Okay, if g diverge, okay, g is smaller than f, of course f also diverge. But there are something that you need to make sure. Okay, first the statement of f greater than g, you need to prove first. Okay, if you want to compare some unknown functions with other functions, you need to prove that this is true. Then you can go for the other statement. Okay. For example, if g is converged, how about f? Not necessarily converged, right? Because g is smaller than f. Okay. Okay. Let me try to give you some how to use this theorem in practical use. question starts with is integral from 1 to infinity of x over x cubed plus 1 dx converge or diverges? So not necessary to find the exact answer if it's converged, what's the result. But this is just to state whether it's converged or diverged. Okay. Well, I think if you try to integrate directly, I think you can use partial fractions, right? You can use partial fractions. Or, um, yeah, not necessary. Okay. But if you look here, what we can do to solve this is looking at this x. Okay. We have x and x cubed. Okay. Now consider we have a function that is x and x cubed, or we can have a function 1 over x squared. We can consider this. Okay. Okay. Of course, if we take this 1 over x squared and compare with the x cubed plus 1, this will be greater, right? Okay, at least greater or equal because of the plus 1 here, right? Okay. We can try to prove that this will be resulting in this, right? Because of integral from 1 to infinity of 1 over x squared dx converges from our initial lecture, right? Then, by comparison theorem, also converges. So the main idea here is to find or to identify what kind of functions that you can compare with. Okay. Okay, let me give you another example. Maybe a few examples, maybe 2 or 3, maybe 2 examples more. Okay, converge or diverge. So, so the steps is probably the first one is to identify what kind of function that we can compare with. And if you're not sure, we need to find the results for the function that we want to compare. For example, if we're not sure 1 over x squared is converted or whatever, maybe we can try to check that first. Meaning we need to take some time to calculate the integral and then compare with this function. Okay. And probably one way to look at this function is maybe we can just separate this square root of x. So we have 1 over square root of x. And we need to know what kind of results from this integration, whether it's converge or diverge. So first we can consider this. Okay. Okay. If you remember, we already have some discussion about this. Okay. So p greater 1 is converge, right? P less equal 1, this will be diverge. And we know that our power is half, which means less than 1. So this integral should be diverged. Okay, should be diverged. And we can try to take into our comparison. At least from here, because of the sign, and the maximum of sign will be a 1, right? So probably this will have at least 2, right? So of course this will be greater. Okay, this will be greater. And because this already diverged, and this will be also diverged. Okay. We can write because of this diverge, because diverge, then this results. Yes. Yeah, we need to check. We need to solve this and try to figure out whether this is greater or less. Probably, probably. Yeah, probably. Yeah, sometimes for the comparison, this will be the main problem, finding the good functions to compare and prove whether it is greater or less. And sometimes if you did some wrong in the process, uh, let's say it's become less, then you cannot have these conclusions, right? Maybe some in the middle process you get a wrong idea, and then the conclusion will be also different from the results, right? Okay. That might happen. Might happen. Okay. Okay. Let me go through maybe one more example, and we can have some review, especially maybe chapter 6. Maybe one more example on this improper comparison theorem. So let's check this integral from 0 to 1 of secant squared x over x squared of x dx, okay, whether it's converges or diverges. So you need to do some calculations at least to find the integral of from 0 to 1 over x squared of x dx. Whether it is converge or diverge, right? By in doing so, we can set up our integral from 0 to 1. We can start with some random p. Okay, we can have p as any number. Okay. And similar what we did in previous lectures, if p equal 1, okay, if p equal 1, okay, we can imagine that this will be from 0 to 1 over x dx. And we know that because of the 0, If we put here, it will be a discontinuity, right? There will be a discontinuity on 0. So we can use a limit, right? We can use limit. So we can use limit. Now it's 0 from the right, right? Because 0, 1, so from the right, okay? So we can have 0, d to 1. Okay, let me solve this and we can have break later. Let me solve this first. 1 over x is ln. You can just write ln and then x. And this is from t to 1. This will be limit. This is ln 1 minus ln t, right? And we know that this will result in a diverge, right? Because of ln 0, okay? We can write this will be a diverge or divergent result, okay? And we may need to check the other p, okay? We need to check the other p. Okay, I think we can have a 5 minutes break. Okay. So tomorrow, will you go to see the fireworks? No, not sure. Usually you go to the 101 or different area? Uh, too many, right? Too crowded. Mm. Mm. Mm, not sure because we need to prove. We need to prove first. So will you go to see the fireworks? Go 101 or no? I think better to go to some. Usually there are several places. When you sit down, you can see the 101 clearly. In the Sunyata. Yes, yes. I also tried several years ago. I tried. Yeah, yeah. But it depends on the clouds. Sometimes the cloud is too much, so if we just only see like a glimpse, not really clear. Yeah, there will be a lot of people, and after finish the after finish, they will be like, one time I go there, and we need to walk from 101 to at least walk, and basically it will be faster if you have like bicycle, park your bicycle somewhere, and you can go ride it return home. Yeah. Because a lot of people like walking really like really long way. Yeah. Yeah, I'm not sure, but I think I will just go nearby if we want, or maybe just take, yeah, take some place and see from higher place. Mm, usually, if you go, you can go to the Sanyatsen. There is like a park, and when you sit on the park, you will see clearly one-on-one. But there will be also many people, but not as much as the one-on-one. And you can bring like maybe some snacks, instant noodles. You can make instant noodles and eat. Yeah, 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 yeah. Yes. Okay, I think we can continue. Okay, now for the other p, we can just write down our limit, and we can just write 1 over x with power of p, and we just integrate as usual. This is minus p plus 1, right? So 1 minus p, and this will be also 1 minus p, like that. Integrated from t to 1. Now we can write still limit. We can take, or we can also actually take outside the 1 over 1 minus p because that is a constant. And we can have 1 minus t, 1 minus p. And we can write this in terms of t, p minus 1, like that. We rewrite in the fraction, in our fraction. And from here, we can think on how p will behave. Like if p is greater than 1 and if p is less than 1. If p is greater than 1, then p minus 1 is greater than 0, which means it's positive. So 1 over p minus 1, okay, this will be getting an infinite result or divergent, right? But when p is less than 1, which means it's this p minus 1 is a negative result, then when we have p minus 1, this will be resulting in 0. So we know that this will be convergent. So if we are looking back on our question here, 1 over x squared of x. So we have from 0 to 1, 1 over x squared of x dx. We can write this as 1 over x 3 over 2 dx, right? Which means the p is greater than 1, right? And when p is greater than 1, as we mentioned, this will be a divergence. And also, you may also, if you choose to calculate this result, you can also do that, and it will be also same result on divergent, right? If you want to integrate this 3 over 2, okay? So I'm showing you the general rules for from 0 to 1. Okay? It's a little bit different from the last one that is from a constant to an infinity, right? Then we can write down that secant squared x over x squared of x, if we compare with this probably will have this, right? Because secant can have 2, right? It can have square root of 2, it can be 2, and it will be greater, right? If you check the pi over 4, we'll have at least a greater, right? So because of this is divergent, then the integrations from 0 to 1 of secant squared x over x squared of x dx also diverges by comparison theorem.